expensive, so I urge you please to fill out that survey to help us out. We'll report results directly to the NSF. We are interested in results for all of you, domestic and international. So please take a few minutes to fill it out. The numbers don't have to be exact. Reasonable estimates. So there are things you don't know, like down to the dollar. That's fine. All right, and with that, I'll turn it over to you.
Perfect. Yeah, so thank you all for coming so early in the morning. So today I'm going to continue what we started last time of talking about how to kind of phrase collider physics questions in an operator language. And so just to remind you, so last time I spent a lot of time discussing this particular, what I call the ANIC or energy flow operator. And so last time we defined it like this as some, what is called the detector operator, which measures the energy flux in some particular direction defined by theta at infinity. And so if you did the homework, you will have checked that this actually does what I said it did, namely that it measures the flux. For example, if you just have a free particle state, that when you act with this on it, it actually measures the energy of that state. And so I said one kind of nice thing about these is that once you have them, so if you have your collider where you produce some excitations coming out, you can now start to measure correlation functions of these objects by putting a bunch of different energy flow operators at different angles. So for example, like this. And this allows you to probe kind of correlations in the energy flux which is coming out, much like you would for like the cosmic microwave background or something like that. And so in particular, what you can measure, or the kind of observables, are correlation functions of a bunch of these different energy flow operators. So you can act with your vacuum, for example, on some operators, which we'll get to in this lecture, to excite some state, and then you can measure a whole bunch of these energy flow operators, like this. And so I said that the reason why this was nice is, on the one hand, this is related to local operators, in particular the stress tensor. And so that allows us to use, for example, correlation functions of the stress tensor that someone else has computed to compute collider physics objects. And then the second is that once you say that what you're trying to measure in a collider is this very specific object, so this is now some well-defined object, which we'll explore more, but once you specify it very precisely, you can now start to use, for example, symmetries or other techniques to study this object. So normally when you study, let's say, jets or something, it's hard to study them using standard quantum field theory techniques. But now that you have a very precise operator definition, you can give this to some, I don't know, formal theorist or something, and they can study the symmetry properties of this object. And so it's very easy to study symmetry properties, which we will do. And so this may seem a little bit abstract. And so in particular, since it's kind of early in the morning, I wanted to show some pictures showing what these things actually look like in real world data. Just to show that they're not just kind of a nice theoretical thing that you can write down, but that you can actually measure them. And so in particular, one thing you could do, so yesterday with Stefan, you learned how to make a parton shower. And so you could literally run this parton shower and then measure this particular object, and it will actually give you plots like the ones which I'll show you in a second. So just how do you actually do this in practice? Or what do these things look like? So one thing you can do is you can produce some very high energy jets at the LHC. So these are something, or you could do them using your parton shower that you nicely made. And so this will have many, many particles. So you can make jets, for example, in the TeV scale. These will have many particles coming out. And then you can literally place, so I think that's my email. then you can literally place these detectors at some specific configurations separated by some angle. So these are these E of theta 1, theta 2, and then what you can do is you can plot this specific cross-section as a function of the shape of these objects here. And so the reason why this is nice, as I'll show you in a second, is that these behave almost like correlation functions of local operators. So you can think of kind of, at least when they're at small angles, you can just stereographically project this to a plane. And so you can really draw these correlation functions as a functions of kind of points in the plane. And then you can study them just like you would for normal correlation functions. And so just as an example of what the type of thing you'll see, so this is a plot of a 4-point correlation function inside some jet. And so what's being done, so since it's now a position, or it's a function of the position of all these different operators, you have to choose some specific projections to look at. So for example, in the one to the left, what has been done is one has fixed the location of 3 of the correlators. So you fix and then you take one in the middle and you move this one around to different positions to kind of probe the structure of the correlation function. And so it's a function of this, the position of this particular one in the middle. And so you can see that it has this fairly intricate shape where it's, for example, very peaked as it becomes close to any of the other correlation functions, or as it becomes close to any of the other operators. And so this is something which is kind of normal for operators that as you bring them together, you expect some form of kind of singularity. And so in this particular case, so this is a singularity of QCD, or in particular of gauge theories. And so does anyone know the name of this singularity, or what this is kind of showing you, the fact that it's very peaked as you bring 2 of these together? Yeah, so this is a collinear singularity. And you can very nicely see it inside the structure of these operators. And so more generally, you can do kind of other things and kind of just play with these. So they're really just, they kind of map out the energy flow inside these jets. And so for example, in the middle, what is being done is a different configuration where one has fixed 2 pairs. So in this one, you have one here and one here. And then you have 2, so you can think of these as kind of 2 dipoles. And you spin the internal ones around as a function of both their size and this angle here. And so you can kind of map out the structure of the energy flow within jets in a very nice way. And so they really give you kind of a little thing that you can play with and study in detail the structure of the energy flow in jets. And so these objects are very nice for visualizing this. And this is something you could literally make using a parton shower. And so these are actually just a toy with a parton shower or something. But if you could do this in real data, you see something very much the same. So you can actually measure this inside real high energy jets at CMS. And so this is one of the reasons that one wants to develop techniques. So this is this configuration where you spin these internal ones. And so you can really kind of map out the structure of the energy flux in QCD. And so the other thing which you can do is you can study them much more quantitatively in specific limits. So I said that, or as someone pointed out, this limit as you bring 2 of the detectors together is referred to as this collinear singularity. And so you can study in much more detail the properties as you bring 2 of the detectors together. So, and we'll go through how you actually calculate these in a bit. But this is just to show the kind of different properties that one might be interested in. So typically, as you bring 2 kind of detectors together, so now it will be as a function of the angle between them. So if this is small. So as you bring them together, you expect some form of singularity. And so in particular, in this case, if you bring 2 of them together, you'll get a power law that goes like 1 over the angle, which is the kind of classical piece. And then this is corrected by a specific anomalous dimension, which for technical reasons is called gamma 3, but we'll learn how to calculate what this is later. And so this is the kind of classical scaling behavior. And this is the anomalous dimension. And so one thing that you can do by very accurately measuring the structure of these correlation functions as they come very close together is you can extract the anomalous dimensions which govern certain properties of QCD. And so this is, of course, very similar to what one does with correlation functions of local operators in, for example, condensed matter systems. And so it turns out that what one can do is actually do this, as we'll show later analytically, is you can bring clusters of these objects together. So you can take, for example, some fixed shape, for example, some equilateral triangle like this, and you can scale the whole thing as a function of its size. So you can kind of approach this collinear limit, but with multiple of these operators. And so now, since this is a different correlation function or a different set of operators, you'll get this same classical behavior, but you'll actually get a different anomalous dimension, as we'll show later. So if you scale this, so if this whole thing is a function, so it has some shape, but you can view it as being if you just scale the overall size, that this will go, again, like 1 over theta. So you're again probing this kind of classical collinear singularity. And then it will have, again, a classical anomalous dimension and a quantum anomalous dimension, which for reasons that we'll get to later, is called gamma 4. So more generically, the anomalous dimension that will appear here is n plus 1 if there's n detectors. And so again, this is the classical. And this is the anomalous dimension. And so one thing one can do to actually very precisely extract the values of these anomalous dimensions is you can take ratios of these particular correlators in their collinear limits. So in particular, what you can do is you can study, for example, a 3-point correlator normalized to a 2-point correlator. And so if I just take the ratio of these two objects, one says that this will scale like a difference of anomalous dimensions, like this. So in particular, in the classical theory, this would be flat, so if you didn't have any anomalous dimensions. And in the quantum theory, what this allows you to do is to essentially read off differences of these anomalous dimensions. So you could do, if you wanted to, you could do higher point correlation functions that they would probe kind of the spectrum of these different anomalous dimensions. And so if you go and do this in real world data, so what you see, this is an actual measurement by CMS of this particular ratio inside extremely high energy jets. And so it's plotted as a function of the energy of the jets shown here. And then what one is doing is measuring exactly this particular ratio inside those high energy jets. And so in the classical theory, this would be exactly flat. And so what this is really probing is exactly this power law shown here. So you can really accurately kind of extract these different anomalous dimensions shown here. So you can really see this kind of quantum behavior as you bring these detectors together. And so this is one of the things that we'll try and understand later, kind of why you get this scaling behavior. Sorry, do you have a question? Yes. Yeah. Yeah. So here, the gammas, so, okay, sorry, good. So your question is, are the gammas constant or do they have a dependence on the kinematics? So in a conformal field theory, the gammas are constant. And this we'll get to later, so that's a very good question. So in a conformal field theory, which is what makes it a little bit easier, these gammas are literally constant. And so this is literally an actual scaling or power law. As we'll see, so since these are the quantum anomalous dimensions, So in general, these gamma n have an expansion in alpha s, in powers of alpha s. And when alpha s runs, the alpha s has a dependence on the angular scale. So in particular, what it's actually probing is kind of the PT of the jet times theta. And so this, you can't tell just in this that it's not an exact power law. But if you actually do the explicit calculations, you'll see that you really need the running of this coupling. But this doesn't modify the kind of general techniques too much. And so I'll generally write kind of this in quotes. But what it really means is that you do the actual evolution, including the running coupling. And so later when we do how to do this using factorization theorems, we'll be able to incorporate that. But at the level of taking this ratio, you kind of can't see by eye that it's not this. So it behaves very much like the kind of conformal limit. But yeah, that's a very good question. Yeah, or?
I'm a little confused. This looks like the ratio of 3-point function to the 2-point function.
Yeah.
I don't understand how you get the second relation and why this should be 1 minus gamma and not half minus gamma.
Good, good. So there's a bunch, so we haven't yet, so these were taken from something else, so we haven't yet done this. So for now, this is just kind of highlighting the behavior that we can hope to expect. So later on, I'll show how one can get this. So this is now really just what I wanted to illustrate before we go into, or kind of to motivate why we want to analyze these objects. And they're actually, so last time I kind of described them as being nice theoretically, but they're actually can be like measured in real world experiments. And then the kind of interesting things which you can do with them are you really have the kind of operators as a function of position. And then one of the main things which is nice is to move them together. And in those limits, it will have this scaling behavior. And what this intermediate thing means, we don't yet know. Yeah. But we will hopefully by the end of next lecture at least, yeah. Yes, sorry.
So the theta here is just is it an angular separation?
Exactly, so it's literally the angle between the two detectors. And so for example, so when these are on like the, when these are on like the celestial sphere, it's really the angle, so I can, if I do like a vector n1 and a vector n2, so I can imagine some collision here, and something goes out in one direction and another direction, I can compute like the the dot product of those and compute the angle between them. So in a hadron collider, I should really use like rapidities and angles, but I'll always just assume I'm kind of writing it as theta, as if it's in like a E plus E minus collider. And at small angles, it won't really matter. Yeah, yeah. And so for this, it's really like you can, for example, fix it to be equilateral, and it's the angle between each of the different detectors. Yeah, so more generally, so in the full shape, so like in the earlier ones, you can plot it as a function of the shape of the detectors, or you can kind of freeze them and study their scaling. So those are the two kind of interesting things which one can try and do. Yeah, sorry, there was one other question, maybe not, okay. And so related to, so these are all expansions in the value of the strong coupling constant. And so one thing which is nice is you can actually use this to extract the value of the strong coupling constant. So this is just an illustration, again, that these are actually like realistic, useful things. And so one might want to understand them better in theory. So if you measure this exponent and you know how to compute this in perturbative QCD, so these are specific scaling exponents, so I'll later show that they're the anomalous dimensions of specific operators. And so these can be computed to very high loop order in QCD or in whatever theory you want. And so one of the nice things about this approach is it takes a specific observable which you measure in a collider, and it says that the thing you need to know is this anomalous dimension. So that's a much simpler thing for you to understand, so you don't need to know the full kind of distribution even of energy, even in these very complicated collider events. It says you just need to know this number, and this number you can compute very precisely. So for example, in QCD, this is known to like 4 loops. So it's known extremely precisely, and you can then use this to extract, for example, the value of the strong coupling constant. And so the nice thing about this is, coming from the CFT perspective, is it tells you the nice thing to look for is this scaling behavior and allows you to extract properties of QCD from that. So just as one other thing that we'll go through, so related to your question, so QCD is not conformal. And so one can ask, so I said in this region which I'm plotting, that has a very minimal effect on the shape of this correlator. But if I plot it for all values of the angle or for sufficiently small angles, so I said here, if I plot this 2-point correlator as a function of the angle between these two detectors, I say that it has this particular scaling behavior. So if I do that, it will kind of go like this, and it will just keep diverging off. So can anyone guess what happens in actual real-world QCD? Or does anyone know why this is not what happens in real-world QCD? Yeah, so confinement happens. And so can you guess what confinement will do to this correlation function? Yeah, good. So confinement, actually this is not a perfect plot, but so confinement will make it turn over like this at exactly an angular scale which is set by lambda QCD. So in particular, this is when lambda QCD, or when PT times theta is approximately lambda QCD. And so one nice thing about this is you can actually see the confinement transition. So if you didn't know the QCD confined, by measuring this correlation function, you can very precisely see that that is true. And another thing that we'll see is that on this side, you can actually compute the scaling, and you just get a scaling for free hadrons. So if you're just measuring these correlation functions in the energy flow, you can kind of see that QCD has some asymptotically free region and then some confining region. So this is an actual measurement by the Elise experiment, also the LHC, where you can see this very nice scaling behavior, which I showed here, which will show how to compute in terms of quarks and gluons. And so this has this non-integer anomalous scaling behavior shown here because it's really a kind of quantum theory. And it has non-trivial higher point correlation functions, so it has these interesting shape dependence. And then you have the confinement transition, which is almost kind of like a phase transition. So you can see it directly in the correlated, or it mimics one at least in the structure of this correlation function. And the degrees of freedom rearrange. And then on this side, you really just have classical hadrons essentially propagating out into your detector. And so here you always have integer scaling, so you don't have anomalous dimensions. It's really just a kind of geometric effect. And you have all trivial higher point correlations, so you don't get these kind of interesting shape-dependent correlation functions. And so this gives you a very nice way of kind of just by imaging the energy flux in your detector, you can kind of see the properties of QCD, like asymptotic freedom and confinement, just from these correlation functions. And so again, just to emphasize that these can actually be done. Yeah?
Should I expect to see this nice shape just looking at one jet, or do I need an ensemble?
No, no, that's a very good. So one of the things about these objects, right, is that they're really an expectation value. So when we write, or in particular like this, or also in the, so we're saying in some state where I have, or I can just write it more generally in some state, the expectation value of this energy flow operator, it really means that I'm taking the ensemble average in that state. So I have to prepare, for example, the LHC, like a large number of jets of a particular type, and then really compute the expectation value in that state. And you can also see this in the kind of definition of this detector. I'm integrating kind of over all times. And so I can just imagine like the LHC running, and I'm just kind of averaging over all events of a particular type. So if you plot it for one particular event, it's just essentially noise. Because you're just taking all the pairs, and they'll just give some like all over the place randomly. And then as you average over many, many jets, it will converge to a nice curve. And so
this would not be useful for tagging.
This is not useful for tagging. And you can understand, so you can compute the kind of event-by-event fluctuations in some sense, because they're encoded in higher point correlation functions, which are like variances. And so by computing those, so if you had, for example, like very strong coupling where the jets are very smooth, then the variances are small. That's just saying you'd get like essentially the same, if it's just uniform, you'll get the same thing on one jet as many jets. But QCD jets are kind of spiky. And so if you plot this on one, you'll get essentially nonsense. Yeah.
Just, you didn't why
Good. Absolutely. So you don't strictly. So you just have to good. Sorry. Yeah. So the question was, why do you have to average? So I said you have to restrict to some specific class of jets. And you asked if it's some universal property of QCD. Why do you have to do that? And so the answer is you don't. But you just want to prepare some. You have to specify the state in some way. And so typically, experimentally, what is done is you say jets of a particular PT. And so that's more of an experimental thing. But more generally, you just have to. You tell me how to prepare this particular state, and then I compute it in that. And so this could be like an E plus E minus with some other operator, whatever you want. It could be in heavy ion. And if you just tell me how to produce this state, then I can compute it. And it's just experimentally what is often done is this state is specified by some like PT, some jet radius, et cetera. And so you compute this state in perturbation theory and then evaluate this in there. Yeah. Any other questions about this? Okay, and then I just wanted to highlight, while we're just finishing up the plots, one other property that one can measure experimentally. So here, what I've been showing so far is focused on this collinear limit. So this is what you can measure at the LHC, where you put a bunch of these detectors inside a single jet. So you have some single jet like this, and you put the kind of detectors inside the jet. But more generally, what you could do, for example, in E plus E minus collisions, is they're really spherically symmetric. And so you can measure these correlators as a function of the full angles on the sphere. So here you really have some kind of local source, and then you really have a nice full sphere. And so you can really measure these correlation functions from having an angle between them that's 0 all the way to pi. So you can have an angle between them that's going from 0 to pi. And so we've already seen, so if I plot this full correlation function as a function of this angle theta, so we'll now go all the way up to pi. And so here, this is really the E plus E minus. So this can be psi bar gamma mu psi that I couple into with some polarization vector. And so we've discussed that in this region, it has some behavior like this, which is kind of universal, and then turns over due to confinement. And so can anyone guess, or does anyone know what it does on the other side as I go towards pi? Or y? Yeah. So one way of thinking about what this is doing is it's saying the fact that I have some collinear singularity here is saying that I have essentially jet-like behavior, so things like to be collimated. And so if I have an E plus E minus collision, I'll essentially have kind of two back-to-back jets coming out like this. And so this side is when I have both of the detectors inside this jet. And so I get this collinear singularity, which, as Stefan nicely explained, is described by these people's initials. But I can also have the configuration where one detector lies here and one detector lies here. And so this will also be enhanced, and it will give rise to a kind of different scaling behavior. So it will look kind of like, for example, like this. And on this side, it's actually coming from quite different physics. And so this will be coming, as we'll hopefully get to. So this is what is called a Sudakov. And as I'll explain later in the lectures, this is coming from the behavior of Wilson lines. So in a gauge theory, this will always go up like this. And so what the hope for or hopefully this has motivated you that these objects, or actually, so I'll show if you actually look at this, for example, in E plus E minus, you get this nice humped structure where you can see very nicely this collinear limit and the transition to confinement on this side. And then you have this Sudakov region here, and again, this transition to confinement at very small angles on this side. Yeah.
So is this only true if you select specifically two jet events?
No. So this is really, so here there's been no selection done. That's a very good question. And so here there's no selection done. So it's same as in this. This is really this 4-point function where this is the operator like the QQ bar operator coupling to the photon. I just put 2 of these at generic angles, and this is the operator that creates the state.
For example, if plus minus 3 jets, I'd expect to see the event shape in that plot.
Good. So this is overall. So one of the nice things about these is you never ask whether it's 2-jet or 3-jet because you have to know. And so you it's where the 3-jet event is kind of contributing is in this region here. So the regions that have nice scaling behavior, which is what we're going to try and understand in the lectures, are in this limit and in this limit. In this region here, you just have to use fixed order perturbation theory. And so in here, it's coming from like 3-jet events, 4-jet events, but they have no kind of nice universal structure. And so the really nice universal structure will be coming as you go towards either of these limits, where it's just dominated by the fact there's a singularity here. It means it's dominated by those configurations. And so the other configurations will, so a 3-jet event will not contribute to this leading scaling behavior here. Good. Any more questions about these? Yeah.
So for the opposite side, if the drop comes due to confinement from the momentum speed, because why would that happen on the other side if the momentums are no longer actually close?
That's an excellent question.
Wouldn't the jet have self-correlations going up, but why would the correlation with the opposite jet go down?
That is an excellent question. So, yeah, good. Yeah, sorry. Yeah. So one question was that on this side, you buy the argument of why confinement makes it turn over. And so on this side, you're wondering why this also behaves like confinement here. And so this is a very good question, which I was planning to get to much later, but I'll just kind of briefly say it in words. So if you compute this thing, there is a big difference between the two sides. And so in particular, if you compute it in perturbation theory, this side, when you plot this, in perturbation theory, it just diverges. And so the confinement is really needed to turn it over. On this side, this Sudakov will actually naturally turn it over in perturbation theory. And so what confinement does is to just kind of change the structure in this region a little bit. And so it's a very different structure. But the reason why you should think about, and we'll go through this again a little bit later, is that it's related to the question that was asked about whether or not these anomalous dimensions are constant or whether they depend on the particular scale. And in both these regions, the reason why, so when you're doing this collision, you should think of always, so there's some hard scale at which you did the collision. And so in the middle region down here, that's the only scale in your problem. So in this problem, there's an angle and a Q. And so in this middle region, this angle is just an order 1 number. And so the only scale in your problem is Q. And so in particular, you're always probing the value of the strong coupling constant at Q. And so that's why you get, for example, 3-jet events in here. As you move to either of these two sides, what happens is that you get a small number in your problem. So as you go to this side, theta becomes small. And in particular, you develop another scale, which is Q times theta. And so as long as you have a new scale in your problem, you have some dynamics at that scale. And so you're going to be probing your theory essentially at the scale Q times theta. And so that's why you're sensitive to confinement, is that you're naturally probing this low scale. As you go to this side, the scale that becomes, or you develop that pi minus theta is very small. So on this side, what you get is a new scale, which is Q times pi minus theta. And because this is very small, you become sensitive to non-perturbative effects. And so you do so, as you say, in a more complicated way on this side than in this side. But the fact that you are still getting alpha s evaluated at some small scale remains true. And so on both these sides, you need to understand something about the structure of confinement to be able to say anything about it.
Why would that other scale, why would there be a probing at the scale Q of pi minus theta? Isn't it still probing at Q of theta?
Good. Okay. This is, yeah, it's a very good question. So this is a little bit of a detour, but it's a good question. So So the way you see, for example, this collinear, so you said on the other side there was this collinear singularity. And so the way that you should think about this is if you just have some single, so let's say I produce some single particle which splits into my two detectors like this, at two specific angles like this. What one should do to understand the scales in the problem is to look at the structure of propagators. And so in particular, this 1 over S12 is the scale of this propagator, and this is loosely 1 over the energy of each of these times 1 minus cos theta, and there's some factors of 2, which I've dropped. And so in the small angle limit, what happens is that this piece goes like theta squared, and so this is like 1 over E1, E2, theta squared. And so this is why you have this behavior in theta, that it grows large. And so when theta is small, you should always think that you're probing the propagator at the physical scale of S12. And so there it's clear, as you say, that as S12, if you drop this below the confinement scale, you're kind of no longer, or your perturbation theory is no longer making sense. And so what you're seeing in this plot is essentially this object confining and turning into like pions and becoming sensitive. So you don't want this less than lambda QCD. So this has to be much, much greater than lambda QCD. And so from this, using the energies and theta, you can estimate where this becomes non-perturbative when theta becomes small. So now your question is why this happens in the other region as the angle goes exactly back to back. And so this is called the collinear singularity. Which is coming from the angle going to 0. So if you look at this propagator, you can see that the other way that this can go to 0 is if the energy goes to 0. Right, so this is just an energy, or there's an energy and an angle. And so the only ways that this can become small is if I either have an energy going small or an angle going small. And so what's happening in the other region is that the the energy becomes small. And so we said last time that the contributions from the energy going small were suppressed by the fact, or by the presence of this energy weighting, which is why it's infrared and collinear safe. But in this E plus E minus case, what happens is you produce, so let's say I'm saying there's a singularity when theta is approximately pi, right? And so what is physically happening in that configuration is I produce one high energy, let's say quark, going in this direction, and one high energy quark going in this direction. And so I'm going to put my detectors on this one. And so the detectors lie on very high energy particles. So they're not being suppressed at all, like this. And there's essentially, or approximately pi between them. And then someone can ask, how can one slightly deflect it away from the value pi? And so the way that you can do this without being suppressed by the energy weighting is by emitting very soft, which is, I can draw in yellow. So you can emit very, very soft gluons off of here. So these have energy that is much, much less than Q, like this. And so what these do is they slightly push this thing away from being exactly back to back. And so because they are very soft, if you look at the propagator here, it has exactly the same expression as this. But now these things can be at wide angles. So this angle here can be large. And so what's happening is you get a singularity as this energy goes to 0. So as this energy goes to 0, you're again probing a kind of non-perturbative regime of this, where you're kind of recoiling these things with some coherent, very soft radiation. And so that's why, again, you get this singularity in the back-to-back region. And so the singularities that we will consider are all either, or the two singularities that we will discuss are these soft and collinear singularities, which are effectively the two ways this propagator can go to 0. And as soon as you have any propagator in your diagrams going to lambda QCD, that's where the effects of confinement will occur. And the way they occur in the two sides, as you said, is very different. But whenever you have that, and this is why, as Stefan discussed, your parton shower has to cut off there and hadronize. And so once it gets to that scale, then you have to incorporate the effects of hadronization. Yes. Sorry. Any more questions on these plots? Perfect. Okay. Or yes.
Why does confinement affect the given smaller vector that is very close to it?
When is so anytime you go below this, yeah, so good. So why does confinement affect very, very, very small? So you're asking kind of why it doesn't, so you believe it affects this, and then why does it affect this, for instance? Good. So what happens when it approaches, so when this scale S12 approaches lambda QCD squared, this is at the like peak of this distribution. And actually it's better if one goes back to this. So you'll see in this region is where S12 is approximately lambda QCD squared. And so here you have no way of calculating. So that's why there's nothing like drawn in the plot. And so that's where you really need to understand like the dynamics of the confinement process. So you're correct in the sense that on this side, you don't need to know anything about the dynamics of confinement. You just need to know that you have essentially like free hadrons coming out. So the confinement process is kind of done by here. It's just that it affects the distribution as compared to over here. But the reason you can have some line here is because you can just compute it for literally like free hadrons. So you just have like a free scalar theory and you compute what this correlation function is and it will give you this line. So on this side, you've kind of gone, let's say, below confinement and you just have like free hadrons like floating around coming to your detector. And so you don't really, you don't need to know any like details of how the confinement process happened, you just need to know that it did happen. Whereas in here, you actually need to know like the details of the structure of the confinement process. But it's just that whenever you're below this scale, you need to know something, like the fact that confinement did happen matters for the plot. Yeah, does that make sense? Okay, perfect. Okay, any more questions? Good. So hopefully these plots have motivated that one can actually use these energy correlation functions which I described to look at real world events and that they have some interesting structure. And so this will then motivate us to go back and understand how to understand the structure of these correlation functions and these singularities from correlation functions. So I'll just turn off this. And how do I? Yeah, thank you. Okay. Okay, so now that we've convinced ourselves that these are interesting, we retreat to trying to learn how to compute them, and we'll build up from very simple ones to these much more complicated ones. And so what we're going to try and do is understand how to actually compute and understand these collider physics from correlation functions. And how to eventually get back to those types of plots. And so what I first want to do is just give like a 30-second overview of how people talk about local operators in conformal theories. So we won't need very much details of this, and we'll build it up as we go. But just to start setting up the language. So CFT terminology. And so I should say, so there are many other interesting reasons to study conformal field theories. In particular, that they occur as endpoints of RG flows. And for quantum gravity using ADS-CFT. And so here I really will not have any time to do them any justice. I really just want to say some of the language and then use them for this particular case. But they're interesting to study more generally. So the main property that we'll be interested in is not necessarily conformal invariance, but just scale invariance. And so the thing that will be important is just to understand how people talk about operators in a conformal field theory. Because these will be what we use to compute these correlation functions and ultimately relate to collider physics experiments. So what we'll be interested in, what people talk about in a CFT, so one can just say abstractly what a CFT is so we'll be interested in what is referred to the spectrum of local operators. So again, this is just some terminology. And so for example, from the conformal bootstrap, this is what people are attempting to get. And so these operators we can write just as some OI, and they'll come along with a delta I, which is their scaling dimension. I.e. just their dimension. And so these delta I that come along with each operator, these define how the objects transform, how these local operators transform under scaling. So these will be very important to understand because these will determine, for example, the scaling behavior as we approach collinear limits. And in particular, so what these do just for local operators is they define how the fields transform. I'll move this off. Under a scaling transformation. And so in particular, if I take my coordinate and I rescale it by some variable lambda, then my operators so they scale like the following. Just like this. So this is just a definition of what this delta means. And so this can just be understood as some renormalization group transformation, which leaves the Hamiltonian correlation functions invariant. And so in a free theory, this is of course just the mass dimension, but more generally, these don't have to be integers. And so typically, or we will work with Lorentz invariant theories. And so in that case, these operators will also have a spin associated with them. So this will also, so you can kind of classify these operators by some spins, some other quantum numbers that you might have, and then the scaling dimensions of your field. And so this is really all we need for the discussion. So one can work out, for example, what the behavior of this, what is referred to as the dilatation operator actually is and all its commutation relations, but we essentially will not need this. Yes? So in here, it depends on the particular operator given here. Yeah, and so here we'll later classify these operators. And so in general, it can depend on it depends on all the properties of this operator. So here, this is really just some index. And then in general, this anomalous dimension can depend on those properties. Yes? Yes. Very good, thank you. And so the other thing which we will always assume, which we mentioned last time, is we'll assume, and these operators will be important in the field theory, we'll assume that we always have a local stress tensor which I'll call T. And we said last time that the scaling dimension of this is always D. So when D equals 4, the dimensions of the stress tensor are 4. And we also did, and so this was used to make, or to at least check that our ANAC operator had the correct behavior. And if we have currents, so we often also have some conserved currents, which are also, so this was like when we made the detector out of the charge. And so we'll write these as J, and these in D equals 4, they have dimension 3, but more generally, they have dimension D minus 1. And so for now, what we can imagine, and what we'll use, is that your friend gives you the spectrum of this conformal field theory. So they just give you a list of operators and anomalous and dimensions. And then they can also give you, and we'll understand how to break them apart into pieces, but we can also imagine that they give you the correlation functions of these operators. So that's kind of what would be phrased as like solving the field theory. And so now what we want to do is to use these and these basic properties to investigate what we can get for collider physics from having some spectrum with different dimensions and these correlation functions. And we'll build up as we go along a little bit more detail about conformal field theories, but for now it's really just as a test bed where someone can provide you these, and then we want to use them for collider physics. Okay. So now what we want to do is to just start building up the kind of interesting things we can compute using these objects. And so here what I'm going to really try and do is to kind of mirror the complexity. So I want to kind of phrase what these are as the complexity of the collider physics type observable and how this kind of goes along with the complexity of the correlator And so this will also organize our thinking of what kind of observables are interesting. So for example, you typically don't start, if you look in Peskin and Schroeder, with like a 100-point correlation function here. You start with very simple correlation functions, and then you build up, so you start with like 2-point, 3-point, 4-point, et cetera, and build up. And so what I want to do is kind of map out what these correspond to on the collider physics side. So we're really going to go through, we'll start with 2-point functions, then we'll go to 3-point functions, then we'll go to 4-point functions, et cetera, and we'll see how each of these gives different things in the collider physics world which we can study. And so this will be kind of very simple things, so this won't even probe the structure of the energy flux. Then we'll see that these are essentially largely fixed by symmetries, and these will just be kind of where energy goes. And then this is the actual interesting one that I was showing plots of. And so we'll slowly build up towards this. Okay, so the simplest one, and if you look in any kind of textbook, what people always start with is the 2-point function. So does anyone know what the 2-point function corresponds to on the collider physics side?
So you mean a 2-point function part of your fields?
Yeah, so these will be, let's say, these can be, so all these operators are generic composite operators, so they don't have to be elementary fields. So they could be like, for example, if a scalar like phi squared, phi to the n, or these could be like psi bar, gamma mu, psi, with some polarization, or any kind of composite operator. So for example, if I take this and measure this, or have this 2-point function, does anyone know what this corresponds to? It's the total cross section, so very good. So the simplest thing which one can do, and so of course this isn't even using these energy flow operators, it's just building towards them, is the 2-point function. So in the CFT side, you take some operator, and I can just imagine for simplicity that it's just a scalar operator, like this. And so in this case, it's a kind of standard exercise, and so I won't go, it's a good thing to do. One can use the scale invariance to fix the structure of this correlation function here. So essentially, by translation invariance and stuff, this just has to go like a constant. If I make these I and I. And by dimensional analysis, or by using these scaling dimensions, this just goes like 1 over x1 minus x2 to the 2 delta. So this is something which one can just fix essentially by mass dimensions of the two sides. And so this is the simplest thing which one finds in any conformal field theory book. And in particular, you can just normalize your operator. So this is 1 if you want. And so what it just gives is the dependence on the separation of the two observables. And so now we want to understand what this is from the collider physics side. And so as you said, this is the total cross-section. And so what we can do is, in the collider physics case, we're not putting down an operator at a particular location x, but instead what we can do, or we're typically injecting some momentum. So what we imagine is we have the operator where we inject on, so if this operator is not real, you have to put the dagger here. You inject some momentum q into this side. And so one can often draw these with what are referred to as cuts. So this kind of produces some complicated state like this. This is your amplitude that you can compute in perturbation theory, or your matrix element. And then you have your daggered matrix element, or its complex conjugate, which you can draw as the mirrored object. So this is kind of a nice way of doing it. So you can think of it as like a braquette, where you just draw your Feynman diagram, and then the reversed Feynman diagram on the other side. Like this. And so this is what you do at, for example, an E plus E minus collider, where you really kind of ping the system with some local operator. And so in particular, the total cross-section, so here one is not measuring anything about the properties of the radiation. You're just computing the overlap of the two states. And so this can be written as just the Fourier transform. So you just have to give it some definite momentum. So this is like the center of mass momentum, for example, energy. So you can make it time-like if you want. Of this correlation function, I'll put a 0. And I can just choose to put one of these at 0, like this. And so if someone gives you the list of operators and the dimensions, you can compute the total cross-sections that you'd see by just pinging these operators. And so in particular, what you predict from this, so you can do this Fourier transform of this, and so what it predicts is the scaling as a function of q. So this is the kind of only interesting variable in the problem, so we don't have any of these energy correlators or anything. And so the only thing that it predicts is that this goes like c times, or just some constant, time q squared to the delta minus 2. So this is a nice exercise to do. And so just for people that want to do this more closely, I'll write down the more precise how to actually do the integral. But this is just a very quick aside of what the actual constant and the kind of I epsilon prescription. So as an exercise, for those that are interested, you can do the actual integral you should be doing with the I epsilons. And we can discuss this afterwards if people want, but like this, just to show that it can be done very explicitly. But the nice thing about this is that it just predicts the scaling as a function of q squared. And so it just says it has a very simple power law with certain anomalous dimensions. And so of course one knows that if you measure this total cross-section at like LEP, it has some kind of spiky behavior from the fact that you have resonances. And so what this CFT is doing is just kind of smoothing it out into a single power law that we can understand very nicely if we give the spectrum of these anomalous dimensions. Yeah?
How could this be a cross-section if its units depend on delta?
Okay. Well, so this is not really, so how can this be a cross-section if its units depend on delta? So this is, you should think of it, you're really pinging with different operators. So it's not like a scattering amplitude in the standard way. And so this should be viewed as some, you have to do some proper normalization to do it. But this is the kind of, it's the overlap of these two states. Yeah, so I'm going to be a little bit sloppy in converting to exact cross sections, but it's the overlap of these two states. Yeah. So yes.
I'm a bit confused how this relates to like the perturbative calculation of this cross section.
Yeah.
So I don't see alpha S. So is this like
Good. So alpha S is just here. So the whole like non-trivial dynamics is what this number is. And so here one can just like normalize it to be 1, because here we'll be focused, and I'll get to the actual number like in a second when we do the 3-point. But here you can just, so what this is saying is, the thing that is typically interesting to focus on is the scaling behavior. And so what the calculation in perturbative QCD is doing is calculating this number. And so another way you can approach it is you can just normalize all your operators so this is 1, and then the interesting thing is in all the 3-point functions.
so this number is like an expansion in alpha S and some transcendental numbers.
Exactly. And so the way you'd really calculate it is by doing this diagram here. And so this is a series in alpha S and transcendental numbers. But the nice thing is that this, and one of the things and so in the 3-point where it's more interesting, I'll show both the like alpha S one. But the nice thing is that this holds like, I've never used perturbation theory here. So this holds exactly in any conformal theory. And so if someone gave you this list of operators, you'd say it scales like this, and this number, ideally they'd provide it to you, or you'd normalize it to 1, and then it becomes interesting in the 3-point. And so in the 3-point, yeah, I'll show the exact like alpha S dependence, yeah. Yeah. Yeah, so this is not a time-ordered one, yes. Yes, very much. So all of these, none of these. So when I wrote like these, none of these are time-ordered. And that is very important. And so I'm really preparing the state, measuring these objects, and then like annihilating the state. And so you can view it as either in perturbation theory or just like a strict, that's why it's a strict expectation value, and you can interpret it like this operator here produces a state in which I evaluate this 2-point correlation function. And so that's it is very, very important. And so that's also why when you compute it in perturbation theory, right, what you're doing, you take your amplitude and you square it with the absolute value. So it's like m times m dagger. And so this is the fact that you're doing like an in, that you have this. You have to be careful about the I epsilon prescription, and so that's why I wrote it in this particular way here, which is a good thing to check. But you can also just, if you just do with normal Feynman diagrams, you can use the normal I epsilon on this side and just the flipped I epsilon on this side, and just like square it at the amplitude level. But yeah, so it's very important. And so that's why you should think of this as preparing the state. Then in the next one, we'll measure some energy correlators in this state. And then this is the conjugate state, which you measure the overlap with. Yeah, so that's a good question. OK, so this is not very interesting for what we wanted to do. So what we now want to do is to move on to 3-point functions where we actually start being able to relate them to the energy flux in the system. OK. But so the one upshot, so if you were given a list of these 2-point functions, you get total cross sections. And so now what we move on to is 3-point functions. And so this will allow us to start evaluating. So now that we have 3 operators, for example, like this, we can view these 2 as creating the state, and then we'll actually have something which is evaluating, for example, the flux. And so this will allow us to actually, for the first time, have some non-trivial kind of collider physics type experiment. So again, what we can assume is that our CFT or whoever friend gives us a bunch of 3-point functions. So that we have a bunch of 3-point functions. And so in principle, these could be computed in any theory that you want. And so the only nice thing about the conformal field theory is it largely fixes the structure of the 3-point function. And so there's a very famous formula which again is in many textbooks, and so I won't reproduce it here, but just showing that if you have, for example, scalar operators, you can use these transformations or invariants under the transformations of the CFT to show that this is given by some number, and it has a fixed dependence and sorry, should be. So the exact details of this don't really matter. All that will be useful is that this essentially fixes the structure for each particular tensor structure that you can have over here. It has some very specific dependence and some number. And so this number is what you compute, for example, in perturbative QCD. And so now this is interesting because now we can view the ones on this side as producing some state, the one on this one is producing some state, and move this into a detector operator and actually try computing something kind of interesting. So in particular, what we want to try and do, and so it will begin very simple and it will not be very impressive, and then hopefully move towards something more interesting. So the simplest possible thing we can do in this language collider observable will be the one-point function of this energy flux operator, which I just described earlier, in a scalar state. So I want to do the one-point function in a scalar state. And so in particular, what I want to do, and I'll write these without writing the Fourier transform every time. So I want to have some operator. I want to stick in my energy flux operator like this. And I can always just normalize it to this two-point function. Again, these are always Fourier transformed as appropriate. And so this I'll define as just the expectation value of this energy flux operator in some scalar state. So you can really think of this as if I kind of ping my system with a scalar, and I now measure on my sphere the distribution in energy as a function of the angle. And so does anyone know what this is? So if this is a scalar operator, so we can first use a just collider physics argument. So I can always, if I work in the rest frame of this scalar, I just have rotational invariance, right? And so it can't depend on the angle of this vector, because this is just a scalar operator. And so this is why this one is kind of not so interesting. So it's some constant over 4 pi. So it's just uniform on the sphere. And does anyone know what this constant is?
Wouldn't that just be related to the total momentum of the particles?
Exactly. So it's the total energy that's injected into your system. So this one, we don't need to use such sophisticated techniques to do it. We can just guess the answer. And so it's whatever momentum I inject into your operator, Q, divided by 4 pi. And so this is nice. One has done this from an operator level, but it's essentially a completely trivial thing. But the one nice thing which one can do, which kind of illustrates a little bit the power of this kind of operator construction, is you could ask, how do you actually prove that it's this total energy? Or what's the analogous statement just by using properties of these operators from the CFT side that fixes this to be Q? And so does anyone know, so intuitively this is obvious, but does anyone know how you'd actually prove this?
Would you get it by integrating n hat times epsilon of n hat, something like that?
Yes, yeah. Very good.
Something like that would need to be equal to P.
Yeah, and so why is that equal to, why is that equal to P? So that's exactly what you want to do. But so the language of that, so that's integrating it over some big sphere. And then what you want to use is that this is a conserved current, and so you can essentially shrink that sphere to being around the operator and measure just the charge of the operator. And so the way you can prove this, which just shows, it's again very simple, but just showing how you can manipulate these operators, is to show that this is just fixed by what is referred to as a Ward identity. So in general, if you have some current, right, you know how to define some charge by integrating it on some surface. You just integrate your particular conserved current, and so this gives you a charge. And so in particular, this object has a commutation relation with objects that are charged under it, where it just gives back the particular charge of the operator. And so now you do exactly what you said with this particular object. So you take this object, you integrate this thing over a sphere, and then you move it and act on the operator, and it will give you exactly that it has to give Q. And so this is written out more in detail in the notes, but I'll just kind of skip over it so that I can get to a little bit more in this lecture. So now the final, or what we want to do, so this is kind of extremely boring because it has no angular dependence. So now what we want to do is to do one slightly non-trivial example with these 3-point functions. And so here we can actually learn something very interesting by doing a kind of very, very simple calculation. So the interesting thing we can do is to give this initial operator some spin. So if it's a scalar, it just has this trivial dependence. And so we can, for example, put a spin 1 current here, and then see what the pattern of energy flux is. So we can use a spin 1 current to create our state. And so two spin 1 currents that are nice is that so in the real world with fermions, we could have this. And if you have scalars, you just have you can couple them to a U1, and you'll get this conserved current. And so now what we want to do is to compute the 1-point function of the energy flux in the states created by these operators. So what I want to do is to take my initial state to be created with some operator, which I'll call O, with epsilon and Q, which you can just view as some particular polarization vector, which you can choose, dotted into one of these currents, like this. And I'll Fourier transform it to give it some momentum. And so this is just a polarization vector like this. And so now the thing that's interesting is I have two different vectors in my system. So the way I can kind of think about this is in my source, I have some little polarization vector here, which I can always choose to be space-like by the fact that this is conserved. And then I have my detector, which is in some direction n hat, like this, where I measure my energy flux. And so now there can be some actual angular dependence of how the energy is distributed on the sphere. And so as a exercise, so that I can get to the answer, so you can use the fact that this is a spin 1 current to write down the most general answer for this by combining the fact that it's spin 1 with the fact that it has to integrate to 1 when you integrate the energies. And you can show that the expectation value of this energy flux operator in this state, that the most complicated dependence it can have, so it again has this q over 4 pi factor, and then you have a 1, but then you have a plus some unknown constant like this. And so this is just so that this piece integrates to 0 when you average it over the sphere. And so this is not fixed by symmetries.
Ian, we're over time.
Okay. I will just say one thing.
By the way, when you write really scrunched up against the right hand of the right side of the board, it's sort of hard to see.
Okay. Yeah, so hopefully it says 1 plus a times cosquared theta minus a third. And so the one interesting thing which we'll be able to take from this is that this actually tells us something very interesting about the value of A2.